Alright, this is the video about 5.3, the relative mass of an atom. In the previous clip, we just talked about the different elements. They are made up of different types of atoms, while different types of atoms inside that they will have different numbers of subatomic particles. And if you just refer to the previous pages on here, you may find that what is the hidden message? The hidden message is that different types of atoms they will have different mass, okay, because of the different number of protons, neutrons, and electrons. But the worst deal is that those, if you take a look on these mass, you may find that these number they are very they are not so exact. So which means that if you want to make a comparison to get to know the mass of an atom, it gives some complexity and it gives much inconvenience because those numbers they are rather not exact, so people would not have any idea to know how heavy that type of atom is when you compare with other elements. Okay, so that's why here comes this topic 5.3, which is we will take a look on the mass of the atom, but we will say the word relative. Okay, relative. So what is mean by relative? And you will, I'm sure that you once you have watched this video, you will get to know more about this term. What is mean by relative? In Chinese, we call that 相对. So something like to compare, right? Compare with something. Okay, we call it relative. So before that, it is much related to some different scenarios about the different types of atoms. Even you talk about the same elements, you may have got different atoms. How different is this? Okay, for example, we have got three different types of atoms found in hydrogen. One is hydrogen 1, hydrogen 2, and hydrogen 3, namely hydrogen, deuterium, tritium. Now, what are these? What are they the same? Is that we have all the three types of atoms. You may see that one here, right? One here and one here. So what is it meaning? They both have one proton, one proton, one proton. But the difference is that you may find here, right? Can you see that? The one here, right? Well, the one here, and here we do not have anything which can be colored as orange. What is that? That is the neutrons. Okay, so we have got 0 neutrons for hydrogen 1, and for hydrogen 2, deuterium, which we have got 1 neutrons, and the 2 neutrons for tritium. Okay, of course, if you want to talk about electrons number, they are still the same, right? Because we have got a number of protons and number of electrons, they are the same. Plus and minus, they are the same. So we will call the atom of the element electrically neutral. So this is what you will say it in the previous chapter. Do you still remember? Okay, so electrically neutral. So I like to spell the word clearly such that you will know what is that. Electrically neutral. Okay, so similarly, one electrons for hydrogen 2 and hydrogen 3. So what are those three? Okay, what is the difference between the three? Is the mass. If you take a look at the mass, it is the lightest. Okay, and go to the hydrogen 2, and finally, it is the heaviest, if you count just one by one. Okay, and because of the difference in the numbers of the subatomic particles. So what is the relationship between the three? We still call them hydrogen. So that's why you will see hydrogen, the atomic symbols they are written as H. And so what are they? We call them isotopes. Isotopes, 同位素. 同位素, that is the definition that must you have to remember. Okay, exam definition, right? Exam type questions, this is one I must say that yearly, right? They will be assessed yearly, annually. So please remember this definition. Isotopes, of course, you don't talk about same element, but another category is different atoms. different atoms of the same element which have the same number of protons, just like this one, hydrogen. We have got one proton, one proton, one proton, different atoms, but different number of neutrons. So you have got 0 neutrons, 1 neutrons, and 2 neutrons. You may find that, which will say yes to this. Okay, same number of protons, but different number of neutrons. So this is what we will say about isotopes. Okay, so if you're going to express them, we will say that hydrogen 1 in long term, or in short form, you may write down like this. Okay, hydrogen -1, hydrogen number 2, and hydrogen 3. Now, although the isotopes or elements have a different mass, because of different mass, they have different physical property, but they will say that they have the same chemical property. Okay, so or even you will say that identical, exactly the same. Okay, so it is rather impossible to separate the isotopes of an element by chemical means. Okay, by chemical means, so you cannot separate it. Okay, but you have got different mass, therefore physical property slightly different. Okay, slightly different physical property. For example, melting point, boiling point, a slight difference, but not so significant when you compare with other elements. Okay, just like 0 point something, or maybe just 1 or 2 degrees difference. For example, you talk about melting point, boiling point. Now, and in the world, do you mean that, Mr. Chin, or all elements they have their own isotopes? Yes, but their abundance is different. Abundance means how much they are. How much do they have relatively when you compare with their own element? Okay, so of course, what is the hidden message? You are going to add those three. We have got 100% carbon. We have got 100% here. Nitrogen, you add that too. We've got 100%. Oxygen, with you add 3. We've got 100%. 100% for fluorine itself. Just only one isotopes. Neon, we have got 2. Added together 100. Chlorine, we have got 2, 100. But they have got different abundance, right? It's not necessary to be 99 to 1. It can be 9 to 1, 90 to 10, or 75 to 25, etc. So that number, so under what principle do we have this number? Sorry, no principle. It is found from the Earth crust. It is found from the planet Earth, right? From the Earth. So say you have to all those, we do not have any data that can be guessed. Okay, it's just by the discovery of those. Okay, so can you get a point? So once again, I need to remind you once again about what is meant by isotopes. Is that they have the same, we call different atoms of the same elements, but they have same number of proton, okay, but different number of neutrons. Okay, so this is what I would like to talk about this. Okay, and because of that, once you know we have got different isotopes, so each of the isotopes can be given a number to tell how heavy it is. Okay, the best way to represent how heavy it is to use an integer, right? When you compare with something like 10 to the power minus 24 gram, right? What you will see in the previous pages to tell you the mass of one proton, one neutron, right? It's quite difficult to comprehend, right? What is mean by that? So we no longer use this data. Instead, we use a rough number to tell you how heavy it is. But of course, we need to take a reference point. What is the reference point? The scientists, they will choose carbon-12 atom as a reference point. It is a standard atom. So how standard it is? One carbon-12 atoms consists of 6 protons, 6 neutrons, and a mass of 12. So we would define carbon-12 atoms, they have a mass exactly to 12.00000. Now remember, you know unit, or you say you have carried the unit, we call it A dot m dot u. We call that atomic mass unit. Okay, so you use this data to replace those non-exact figure times 10 to the power minus 20 something. Okay, because this one it is too difficult to comprehend. But once I write down 12.00000, and we will get a rough idea on how heavy it is. It's just a reference with this number. If you have got a number smaller than 12, which means that atom is lighter or less heavy than one carbon-12 atom, or else heavier. Okay, so it is just that simple. So we will call this one as standard data. We call that relative as isotopic mass. We talk about one isotope. Okay, you use this reference and do the proportion to tell. So what does it mean by that? For example, hydrogen atom, hydrogen 1 atom, they will have because they have the 1/12 of the mass of a carbon-12 atom, so the relative isotopic mass is just 1. Okay, it's easy, right? So this is 12, carbon-12, relative isotopic mass of carbon-12 is 12. So hydrogen 1 is 1. It's easy. So how about magnesium? Magnesium will have got the relative isotopic mass equals 24. Wait a minute, Mr. Chin. Do you mean that the mass number? Yes. You may say so, right? Because they are the same, right? Can you see that? They are the same. If you circle that, you make it the same. Even you talk about carbon-12, right? We have got 12. Okay, 12. So you may say that the relative isotopic mass is just the same data as its relative if its mass number, right? Yes, that's right. So very similar to mass number, but of course they are talking about different concepts. Okay, so first of all, mass number, I count it as number, of course. I count the number of what? Number of proton and neutrons. But if you talk about relative isotopic mass, for example, that 135 for chlorine 35, which means that 35 it is a relative number, the relative mass, okay, when you compare with carbon 12. So we have got that the atom of an isotope, relative mass of that isotope. So this one, it is just the data to tell you how many times it is nearly 3 times heavier than one carbon-12 atoms. So you use that data. While for mass number, it just count number of protons and neutrons. Okay, so do you mean that one nitrogen, but not one neutron or one proton, they will have got a relative mass of 1? Oh yes, very good. Okay, maybe you get the point. One proton or one neutron, they will have a relative mass of 1 unit, 1 at AMU. Yes, that's right. So you use this concept to relate more about the for some elements which have different isotopes. Okay, so it is quite difficult to search in bulk. Okay, some of them they are heavier isotopes, one of them is lighter. So that's why we come up with another concept. We call that relative atomic mass. So you just randomly pick up, for example, 100 or 1000 atoms of having their own percentage of different isotopes, making that element. So in bulk, they will have a certain mass, okay, which comes from the contribution of heavy isotopes with their abundance or lighter isotopes with their abundance. So because of them, they are not equally distributed or equally with that the same percentage of abundance. So you need to calculate as a weighted average. Okay, you need to consider the relative abundance as well as their own relative isotopic mass. So you add it together. Okay, so we'll call that weighted average 按比例平均值。Okay, 按比例平均。So maybe that idea maybe is quite new to you, but every year you need to deal with this. It is very similar to what you are having as the aggregate marks in your in each year. 全年總分. So you very similar. How similar it is? Well, you know the aggregate marks, they will be divided into several parts, right? In our school, so we may find that CA1 15%, CA2 15%, half year exam it is 25%, or the final year exam is 45. Suppose for IS we have got different marks. For example, 100, 110, 120, and 130. So what is the final marks? Is it just added together 100 plus 110, 120, 130, and then over 4? The answer is no, because for 130 marks, it weighs heavier. Okay, so that's why the weighted average is something like this. How do we calculate the aggregate mass? It seems like this. Okay, you're going to multiply that, multiply that, multiply that, multiply that, and make a sum. So after calculating, here comes the aggregate marks. Okay, you add it together. So similarly, you are going to calculate something similar. So for the relative atomic mass of an element is a weighted average relative isotopic mass of all the naturally occurring isotopes on the elements on the carbon-12 scale. Remember the carbon-12 scale? 12 on 0.00000 scale. Okay, so afterwards, what we are going to do is to have some mathematics. We have got two examples that maybe appear in your exam. First one is to calculate the relative atomic mass of an element with a given relative abundance. Okay, so I would like to let you know what is that by circling with different color. For example, chlorine 35, the abundance is 75%. How about the second one? Second one is chlorine 37. We have got 25%. So how the task is to calculate the relative atomic mass of chlorine. As said before, it is a weighted average, the relative isotopic mass of the isotopes, which means that you are going to calculate chlorine 35 with the 75%. Now, just like what you're having while you do the aggregate mass, right? And then what? Plus, okay, plus 75%, 37 times 25%. Can you see that? You add together. And finally, here comes 35.5. 35.5. So what is the hidden message? It seems like using the mathematics concept, and you can get what I mean, right? So we have got 35, 36, and 37. In case we have got the relative abundance of the two being 50%, 50% for that two isotopes, for example. So what will be the weighted average? You may know that it is 36, right? You know that 50-50. So we have got it seems like we have got these lines. Okay, so what you are going to do is to divide it. 1, 2, 3, 4. 1, 2, 3, 4. All together 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, 5. Therefore, 5 written here or 5 written here. What is mean by 50-50? You are going to fight against each other and try to come up with that. That is the weighted average. If you are having that two 50-50. Can you get a point? So what will happen if I'm going to have chlorine 35, it is 75%, okay, while for chlorine 37 it is just 25%. Okay, so what does mean by that? Well, we have got this one a heavier weighting, so that point, the weighted average point here will be shifted towards more on those 35, okay, how much? They will shift it as 75%, and this one is 25%. Then come back 25%, which means that 75 to 35, it is just 3.3 to 1, right? 3 to 1 ratio. So what is in the message? You are going to divide it. Okay, you are going to divide it into 4 parts, and you are going to have the 1/4 here, 1/4 on your left hand side. Or in other words, some of you would love to use 75% and 25%, which means that you are going to count the number 1, 2, 3, 4, 5, 6, and 7. 7.5. Can you see that? And we have got 2 to 25%. 2.5. So this is where it is the weighted average. It is when you compare with that 75% and 25%. What is that? What is that? Yes, that's right. It is, okay, it is 35.5. It's just the midpoint of 33, 35, and 36. Yes, that's right. So you have to either use the concept in mathematics, or you just simply do the calculations like this, and you can get the same idea, right? You can say the same answer. So remember, you are going to correct the answers to the 3 significant figures. Okay? How about question 2? Question 2, you are going to do it in reverse. So we have got the neon. That it has 2 isotopes, neon 20 and neon 22. So remember, you are going to use these 2 numbers because it refers to mass, atomic mass, relative isotopic mass. So the relative atomic mass is 20.2. You are going to calculate relative abundance of the isotopes. Remember, you have got their own percentage. You have got their own percentage. You add it together. Here comes 100%. So that's why you are going to, let's say you are going to let neon 20 will have got the abundance of Y, while you use we use neon 22. Neon 22 we've got abundance of what? 1 minus Y. So why do we use that to use that too? When you add it together, what is that? Y plus 1 minus Y, which is equal to 1. So what is mean by 1? 1 means 100%. Can you get a point? So Y, what would be expected to be the beta of Y? Y should be ranging from 1 to 0. The data between 1 to 0. We've got a 0 point something something data, right? So you are going to use this and change it to percent. How? Times 100. Times 100%, and you can get the data. Can you get the point? So the relative atomic mass of the neon is 20.2, and you are going to do the same thing. The same thing. I count is 22 times 1.1 minus Y, and second is what? 20 here times Y. You add it together to form 20.2. You add it together, 20.2. And 20y plus 22 minus 22y is equals to 20.2. And you exchange the terms, okay? Those 22 come here, right? And you may get what? You may get 2 minus 2y, okay? Equals what? Minus 1.8. So we will get this data, right? So you divide it by 2, minus 2, you may get y is equal to 0.9. So you're going to express the answer as 3 suffix, so remember to put that 0, 0. And by doing so, what does it mean by that? Y, it belongs to the relative abundance of neon 20. So the neon 20, we've got 90%, 90.0%, while for neon 22 is 10%. Remember to check the 2 numbers. 90% plus 10.0% equals what? Equals 100%. Okay, you're going to get something like this. Is that clear? So if you found it has an easy start, I'm sure you have no problem while you do the the class practice in the next page. Okay, so shall we take a look on the next page? Now, checkpoint. Magnesium occurs naturally in three isotopic forms. The relative abundance of each of those isotopes is shown in the table below. So what does it mean by the isotopes of an element? So remember, this one, it is frequently assessed. No need to ask whether or not this one will be assessed in this exam. Okay, a must for that. So what's mean by the isotopes? Isotopes means what? No, so remember, you have to memorize the whole term. Refers to the different atoms of the same element. Okay, remember, same element, yes, that's right, but you are going to talk about under the same element, they have got different atoms, which have what? The same number of protons. Now, you have to memorize they have the same number of protons. Otherwise, it belongs to different elements, right? Same number of protons, same element. But they have different mass, right? But they have different number of neutrons. So that's why, right, that is 12 proton here. All three they have of course 12 proton, but we have got 12 neutron for magnesium 24, 13 neutron for magnesium 25, and 14 neutron for magnesium 26. Okay, so we will tell what does it mean by A. Is that clear? So we have got B, relative atomic mass. You have to calculate the magnesium. So you are going to write down something like this. LAM of magnesium, it is just a weighted average. So what you're going to do is to refer to the data here, right? So what's that percentage? Okay, so to start with, it is 24 times 78.6%. Okay, and then what's next? Yes, that's right. You are going to get this, right? Magnesium 25. So 25 times 10.1%. And what's next is to have magnesium 26, okay? 26 times 11.3%. So remember, what is that? Weighted average, so you make a plus here. Okay, only by having this, I calculate up to 100%, right? You can get what I mean. So we have got 24.3. What is that? No unit, remember. No unit for this data. No unit, no need to write anything. Remember, put down the gram. If you write down gram, sorry, no marks. It's easy, right? How about C? Is it possible to separate the isotopes of magnesium by chemical means? Explain your answer. The answer is no. Why? Why not? Why not? It is because isotopes have the same electronic arrangement. Okay, same electronic arrangement. So they have the same, or you use the word identical, chemical property. Now it comes to the people concerned, right? What's mean by same electronic arrangement? So for magnesium, those 12 atoms, they are placed in their own order. Okay, the order should be for the first shell, they have got 2 electrons. Second shell, we have got 8 electrons. Altogether, we've got 10, right? How about the remaining 2? Remaining 2 atoms, they will replace it on here, okay? So no matter it is magnesium 24, 25, 26, they have the same electronic arrangement. Or some shorthand method to represent electronic arrangement of magnesium, it is just by writing down as 2, X, and 2. Okay, we have got the same. Okay, so they have got the same or using identical chemical property. So it is for C part. Okay, it's easy start. How about question 2? Question 2 a little bit more difficult because you are going to find out some unknown. The unknown is the relative abundance of the isotopes. So this time you use another element as example, boron. They have got 2 isotopes, boron 10 and boron 11. So the relative atomic mass, the weighted average is counted as 10.8. 10.8. So you are going to calculate relative abundance of the isotopes. So first, the first step, you're going to let the relative abundance of boron 10 be Y, then that of boron 11 is about is 1 minus Y. You can get the point, right? Once again, we have got 2 isotopes for boron. Y plus 1 minus Y equals 1. 1 means 100%. Yeah. So what is that? What's next? Relative atomic mass of boron is calculated as what? 10.8. How could you get that 10.8? You're going to find it as a weighted average. You're going to find out the weighted average relative isotopic mass of all isotopes. So what is that? You write down 10.8 again, and you put them one by one. Boron 10, Y, okay, 10Y, and then what's next is here, boron 11, it is 1.1 minus Y, okay, 11, 1 minus Y. So what's next? You add it together, and you can get 10.8. So what's next? 10Y plus 11 minus 11Y is equal to 10.8. And you put the Y term here and put the integer term, the number term or constant term here, right? No Y here. So what will you get? It is just minus what? Minus Y equals minus 0.2, right? 0.2, which means that Y equals 0.2. Because the data should be corrected to 3 significant figures, so you have to add 2 extra O here, right? To tell you you are going to correct to 3 sig fig. Okay, so what is the answer? Y refers to boron 10, so the relative abundance of boron 10 is what? Y, it is 20.0%. Okay, and that means the relative abundance, right? I'm so lazy to write down boron what 11 is what? 1 minus Y, which means 80.0%. Is that clear? Now you're going to answer this one. Relative abundance of the isotopes. You're going to find out. Okay? Is that clear? How about question 3? Question 3. An element X has an relative atomic mass of 87.0. At no atom of X has its relative mass. Explain. Yes, of course, yes. We do not count it as a decimal, right? So why? Why have got a decimal? Why isn't it an integer? Yes, originally relative isotopic mass is an integer. So why? Because they has what? Isotopes. They have different masses, right? They have isotope different masses. So you are going to tell me is relative atomic mass. How can you get this data? Yes, that's right. It's just the weighted average. The isotopic masses of or naturally occurring isotopes on the carbon-12 50, right, scale. Is that clear? So you may find this one is just the weighted average. The keyword is the word weighted average. Okay, is that clear? So sorry, this means no, I need to write down 1 hour, right? 2 hour, double hour. Okay, you will find it easy. So you may have more exercise in your supplementary exercise, or maybe in the quiz. And this one you have to do. You have to get to know how to calculate, as well as some explanation parts. Okay. While the checkpoint, the class practice already covers the essentials of what will be assessed in your exam. So I'll just stop here and I'll see you guys on the next video. We'll try to talk something more about how the electrons they arrange. What I mean is something like this, okay? Magnesium, for example, magnesium, I arrange it like this way. So how about the other elements? So we will come to 5.4 in the next video. See you later.